Hello. Today we're going to be going through this exercise from a number 3 textbook, chapter 1. It asks us to show that there does not exist a Pythagorean triple where all x, y, and the z are primes. So a Pythagorean triple is a triplet of integers such that x squared plus y squared is equal to z squared. Okay? And wants us to show that not all three x, y, and z can be prime. Okay? So in order to do this, I'm going to make an interesting observation about the parity of this equation, okay? So we know that prime numbers are either odd or 2, right? So either the prime number is 2 itself or it's an odd number. Otherwise, it would have 2 as a factor and it would not be prime. So what does that mean for this equation in terms of Pythagorean triplets? Well, if I have, suppose I have 3 prime numbers, p1 squared plus p2 squared is equal to p3 squared, okay? Then suppose that none of these prime numbers are 2, okay? And this would mean that this is an odd number squared plus odd squared. And an odd number squared is always odd. And so we'd have an odd plus an odd, and this would end up being an even number on the left-hand side here. Whereas on the right-hand side, we would still have an odd squared as an odd. And so this is a contradiction. Basically, if I don't have 2 in any of these primes, then I'm automatically going to have a contradiction due to the parity of both sides of the equation. One side would force to be even, while the other side would force to be odd. Therefore, we know that if indeed there is a prime triplet, one prime must be odd. Okay, so by parity, either P1 or P2 equals 2. Now, obviously, P3 can't equal 2 because that's the smallest prime number. We don't really count 1 as a prime number. So I can't have the smallest prime number be on the right-hand side of this equation because it's strictly greater than the sum of the other 2 primes on the left-hand side. All right, so without loss of generality, let's assume that without loss of generality that P1 is equal to 2. Well, now I have this equation, 4 plus P2 squared is equal to P3 squared. Okay, well, we know that, in fact, P3 is going to be greater than P2, right? And so greater by how much? Well, it has to be at least 2 digits larger. So P3 must be greater than or equal to P2 plus 2. Why is this the case? Well, if it's equal to P2 plus 1, then it's even, because P2 is odd, right? So immediately, because P2 must be an odd number, we can't just add 1 to get P3, because then we get an even number. So we have to at least be adding 2 to get to P3, okay? What that means is that when I square P3, okay, then I can consider squaring the expression P2 plus 2, and that's going to give me P2 squared plus 4P2 plus 4. So immediately I see that P3 squared has to be greater than P2 squared plus 4. Strictly greater, in fact. And by this strict equality, we can easily conclude that that this here cannot hold. This is a contradiction. Okay, because we've shown a strict inequality between these two terms. And so that's it. That's the proof. Pretty straightforward. As long as you recognize this parity argument, because once you recognize the parity argument, you can simplify very significantly. Without this, it's there's possibly a lot more different arguments you could make. So maybe try to come up with your own proof for this statement and maybe post it in the comments, and I'd be interested to hear what y'all come up with. Until next time.